7 minutes ago, the James Webb Space Telescope stared into a patch of sky no human eye had ever meaningfully seen, and the picture it sent back broke something in the software astronomers use to understand the universe. The light had been traveling for almost the entire history of time. It left its source when the cosmos was younger than a toddler, when the first stars had barely finished forming, when the first galaxies were still lumps of gas shaking themselves into shape. And when that light finally arrived at a mirror 6.5 meters wide, floating 1.5 million kilometers above the Earth, it carried a message that no model, no simulation, no carefully written textbook had ever predicted. A galaxy was sitting there, small, bright, reddish, already large, already mature chemically, already holding stars that looked older than they had any right to be. And the date stamped on the discovery, May of 2024, made the shock worse because this was not the first time Webb had done this. It had already done it again and again. Each new image arrived with the same quiet rumor. Cosmology is broken, and nobody knows exactly which piece. Stay with me, because the part nobody is talking about comes at the very end, and it has to do with a recent paper from 2025 suggesting that what we are seeing may not be galaxies at all. They may be black holes pretending to be stars. And if that is true, the entire story of how the universe grew up has to be rewritten. To understand why anyone would call this the moment physics stopped working, you have to go back to what astronomers thought was true before Webb launched. The story went something like this. The universe began with the Big Bang almost 14 billion years ago. For the first few 100 million years, there were no stars. There were no galaxies. There was only a hot fog of hydrogen and helium, cooling slowly, until gravity pulled the gas into clumps. Those clumps became the first stars. Those stars exploded and seeded the darkness with new elements. Those elements cooled into fresh gas that pulled itself together again into the second generation of stars. And so on. Each generation built a little more structure, a little more chemistry, a little more light. Models built on this picture said something very specific about how bright the first galaxies should be and how large they should be by a given moment in cosmic history. Look at the universe when it was only 300 million years old, and you should see a sprinkle of tiny, faint, irregular galaxies, almost invisible, just beginning to glow. That was the prediction. Almost every model agreed. Almost every textbook agreed. And almost every astronomer working on galaxy formation agreed. Then Webb opened its eyes. The James Webb Space Telescope did not arrive quickly. It was first imagined in the late 1980s, shortly after the launch of the Hubble Space Telescope. Engineers and astronomers at NASA had already begun wondering what would come next. The Hubble could see visible light, and a little ultraviolet, and a little near-infrared. It was a giant leap, but the universe's earliest eras were mostly out of reach, because the light from them was stretched into the mid and far infrared by the time it reached us. So in 1989, a task force inside the space science community sketched what was then called the Next Generation Space Telescope. The name changed over the years. The budget changed over the years. The launch date changed more than a dozen times. The mirror size changed at least twice. Partners changed. Politics changed. Funding crises nearly killed the project in 2010 and again in 2011, when a congressional panel recommended cancellation before a final redesign saved it. Through all those years, the basic idea stayed the same. Build a telescope with a primary mirror several times larger than Hubble's. Park it far from Earth, where the warmth of our planet's atmosphere cannot pollute the infrared signal. Give it instruments that can split that infrared light into spectra and read out the chemical signatures of whatever emitted it. And point it first, before anything else, at the faintest, reddest, most distant objects in existence. After more than 2 decades of design, redesign, delay, and rescue, the renamed James Webb Space Telescope lifted off from the Guiana Space Center in French Guiana on board an Ariane 5 rocket on December 25th, 2021. It was a Christmas launch, watched by thousands of engineers and scientists across the world. 26 minutes later, separation was confirmed. The observatory was finally free of the rocket, sailing toward a point in space called the Second Sun-Earth Lagrange point, where the gravity of the Sun and the Earth balance in just the right way to let a spacecraft hold a stable position with very little fuel. The trip to L2 took about a month. In that month, Webb executed a long, careful sequence of deployments that had been rehearsed on Earth but never in space. The sunshield unfurled in 5 carefully tensioned layers. The secondary mirror swiveled into place. The iconic honeycomb primary mirror folded open petal by petal, 18 gold-coated segments locking into a single optical surface 6.5 meters across. Every single step had to succeed. There was no way to send a repair crew if any of it failed. When the final latch clicked into place, ground controllers in Maryland sat back and let out a breath they had been holding for years. Webb was whole. Webb was at L2. Webb was ready to be calibrated. Calibration lasted about 6 months. The mirrors were aligned to a precision measured in nanometers. The The instruments were tested against known astronomical sources. The first official science images were released in July of 2022, and the world was treated to the deepest infrared view of the universe ever captured. One of those images, called the first deep field, was pointed at a patch of sky no bigger than a grain of sand held at arm's length. It was filled with thousands of galaxies. Each smudge was a star city, some of them almost incomprehensibly far away. That single picture already promised a revolution. And then the real survey started. SEERS, the Cosmic Evolution Early Release Science Survey, opened early. JADES, the JWST Advanced Deep Extragalactic Survey, opened soon after. The Cosmic Dawn Survey, Cosmos Webb, opened later. Each one aimed at the same basic question: what did the first galaxies look like? When astronomers pointed Webb at a small patch of sky, the kind of patch that would look entirely black to your eyes through any backyard telescope, the images came back full of tiny red smudges. Galaxies, hundreds of them, more than expected, brighter than expected, some of them remarkably old. Inside months of starting science operations, the telescope was already producing prize finds. One team, working on a survey called SEERS, the Cosmic Evolution Early Release Science Survey, found galaxies at redshifts higher than anyone thought possible from such a small patch of sky. Another team, working on the JADES survey, identified the current record holder. Its catalog name sounds like a serial number from a warehouse, JADES GSZ 140. Its redshift, a measurement of how much the light from it has been stretched, sits at 14.32. That number is not a typo. A redshift of 14.32 means the light we are seeing left that galaxy when the universe was roughly 290 million years old, less than 2% of its current age. When JADES GSZ's 14.0 emitted that light, the cosmos was still in what astronomers like to call cosmic dawn. And yet the galaxy in that picture is already luminous, already structured, already actively forming stars. That does not sound dramatic until you understand the math. The standard picture of how galaxies grow says they start tiny. They grow by collision and by pulling in fresh gas. Each new generation of stars adds a little light. A galaxy in the universe at age 290 million years should be on the small side. Definitely not as bright as a galaxy 10 billion years old. Definitely not as chemically enriched. Yet JADES GSZ 14.0 and its cousins keep showing up looking too bright, too chemically mature, too structured for their supposed age. They are galaxies that look like teenagers, while the cosmic clock says they should still be toddlers. That is the first part of the puzzle. The second part is something even stranger. Telescope teams began noticing that a huge fraction of the early galaxies Webb was turning up shared a peculiar look. They were compact. They were reddish. They were very small on the sky, smaller than the camera's resolving power could fully make out. Astronomers started calling them, almost affectionately, little red dots. The name stuck. Tens of thousands of them have now been cataloged. They show up in every deep field Webb takes. They show up at redshifts between roughly 5 and 15, which means we are seeing them across the first billion years of cosmic time. Some are extremely bright in infrared. Many of them flicker or vary in brightness. Many of them show broad emission lines when their light is spread through a spectrograph, meaning the gas inside them is moving very fast. And the speed of that gas is one of the signature fingerprints of supermassive black holes. That last detail is what tipped a careful, slow-moving community of researchers into something close to panic. The little red dots, on average, look like they are hosting supermassive black holes that are wildly out of scale with the galaxies around them. The mass of a typical supermassive black hole at the present day is roughly 1/10 of 1% of the mass of the stars in its host galaxy, a roughly 1 to 100 ratio. In the early universe, most models expected that ratio to be even smaller. Black holes were supposed to lag. Little red dots, if they really are black holes, show ratios in some cases close to 10% or even higher. A black hole 10 times more massive than it had any right to be, and a galaxy 100 times smaller than it had any right to be. That is the image. Two things at the wrong scale, in the wrong place, at the wrong time. This is what physicists mean when they say, in plain language, something is not working. The numbers come out and the numbers do not fit. The pieces do not interlock. The story the universe should be telling is not the story the telescope is hearing, and this problem does not stop at the early universe. It cascades forward into nearby galaxies, into the present-day distribution of black holes and stars, into the calibration of how fast the universe is expanding, into how heavy elementary particles are allowed to be. A crack at redshift 14 does not stay a crack. It propagates. Now this is where the paper from 2025 lands, and it is the part of this story that the headlines have barely touched. A team of researchers, including the astrophysicist Francesco Paccucci and collaborators at institutions including Harvard and the Max Planck Institute, set out to ask a careful question. What if the little red dots are not really galaxies in the normal sense? What if the bulk of their visible light is not coming from stars at all? What if it is coming from the supermassive black hole itself, glowing inside a dense shell of hot, ionized hydrogen? They called the resulting object, in technical language, a black hole star. The name is not a metaphor. In their model, the black hole sits at the center, pulling in gas, glowing hot, lighting up the surrounding cocoon of plasma. From far away, the system looks almost like a compact, intensely luminous star cluster, yet it is not stars. It is a black hole dressed up to look like a galaxy. If that interpretation is right, the galaxies we thought we were seeing in the early universe were never galaxies at all. They were black hole stars. And that is a fundamentally different picture of how structure formed in the first billion years. It would mean the first bright sources of light were not enormous collections of newborn stars. They were voracious black holes with a glowing skin around them, lighting up the dark long before most stars had a chance to get going. It would mean the universe got its first big blasts of light from gravity rather than from fusion. It would mean almost every model of cosmic dawn would need to be redesigned to put black holes first and stars later. This is not yet a settled question. Another camp of researchers, publishing in Nature in 2025 in the same months, lays out a different reading of the same data. They argue that little red dots are still real galaxies, but galaxies whose central black holes are unusually massive for their stellar hosts. Their picture is sometimes called the AGN cocoon model, where AGN stands for active galactic nucleus, the technical term for a feeding black hole at the center of a galaxy. In their model, the little red dots are young galaxies wrapped in dense ionized shells of gas that hide the normal starlight and reveal the black hole's glow instead. Both teams, in their own way, agree on the same awkward conclusion. The black hole is doing more of the visible work than anyone expected. The stars may be almost a sideshow. There is also a third option that has been gaining ground quietly across 2024 and 2025. Maybe some of the little red dots really are ordinary young galaxies that simply grew very fast. Maybe early stars were much more efficient at forming than older models assumed. Maybe the gas reservoirs around the first galaxies were richer, denser, and easier to convert into stars than anyone thought. Maybe there were simply more stars per unit of mass than the math had allowed. That option does not erase the black hole problem. It just moves the shock to a different part of the puzzle. Either way, the numbers are off, and the disagreement is real, and the disagreement is healthy. It is exactly the kind of disagreement that pushes science forward, the way it pushed the field forward the last time telescopes were this powerful. The shock does not stop with the early universe. While Webb was quietly shredding the story of galaxy formation, another crisis was already simmering across cosmology. It is called the Hubble tension, and it has nothing to do with the Hubble Space Telescope directly. The Hubble tension is a disagreement between two ways of measuring how fast the universe is expanding today. One method uses the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in existence. The other method uses exploding stars called Type 1a supernovae in the nearby universe. Those two methods have given slightly different answers for the past decade. The gap is small, maybe 5 or 6%, but in cosmology, where measurement precision is the whole point, a 5 or 6% gap is enormous. It is the kind of gap that either means one of the methods is hiding a mistake, or means the universe is doing something genuinely different from what our physics describes. When Webb joined the argument, it did not calm the tension, it sharpened it. Supernovae measured by Webb in the near universe with the telescope's sharper instruments refined the high end of the measurement and made the gap with the early universe measurement slightly worse. That has triggered a wave of papers proposing solutions. Some propose that dark energy, the mysterious pressure that seems to be accelerating the universe's expansion, was stronger in the early universe than it is now. Some propose that there is more matter in the universe than we thought. Some propose new forces. Some propose black holes. Some propose a kind of early dark energy, a brief surge of cosmic acceleration shortly after the Big Bang that gave the first structures a head start. Some propose that we are misreading the supernovae themselves, that the explosions we have been using as cosmic yardsticks are not as uniform as we thought. None of the explanations has yet carried the field. The Hubble tension remains alive, well-funded, and unresolved. What all of these stories share is that they point to the same conclusion. Our model of how the universe works on the largest scales, called the Standard Cosmological Model, sometimes nicknamed Lambda CDM, is failing in several places at once. The early galaxies are too big, too bright, too rich, too red. The black holes are too massive for their hosts. The expansion rate disagrees with itself depending on how you measure it. And the deeper astronomers dig into Webb's infrared images, the more often they come back with, look at this, none of this was supposed to be here. So how is the scientific community reacting? In a way that sounds strange to anyone outside science, the reaction is close to excitement. A broken model is not a failure, it is a doorway. Every time a prediction fails cleanly, it tells the field that the next step is waiting just past the door. The little red dots have sparked an entire mini-industry of new observations, new simulations, and new ideas. Multiple teams have applied for additional Webb time to follow up specific targets. Multiple papers in 2024 and 2025 have reanalyzed the same data in different software packages to test whether the strange measurements survive different assumptions. The Hubble tension has produced an equally intense wave of reanalysis, with new instruments on ground-based telescopes and on Webb being designed mostly to pin down which side of the tension is right. The pace of papers on these topics has exploded. The number of conferences devoted to cosmic dawn and to the Hubble tension has multiplied. Yet beneath the excitement is a quieter, more difficult feeling. Some of the most senior people in the field have started saying aloud what used to be considered impolite. They say that we may need more than a tweak to fit the new data. They say we may need a new ingredient. They say we may need to retire pieces of the picture we have believed for 30 or 40 years. Those are not small statements. They are the kind of statements that reshape how textbooks are written and how new students are taught. They are the kind of statements that also sometimes lead nowhere, because the new data can sometimes be reabsorbed into a cleverer version of the same old picture. The next few years will decide which it is. And there is something genuinely moving in the timing. Webb was built for a long list of questions, including the chemistry of exoplanet atmospheres, the assembly of the first galaxies, the growth of the first black holes, and the calibration of deep cosmic distance ladders. It cost more than $10 billion to build. It involved thousands of scientists across dozens of countries and decades of planning. It launched in the final days of 2021 during a pandemic, with engineers in masks watching the rocket leave the coast of South America. And now, just a few years into its science life, it is doing exactly what its designers hoped it might. It is rewriting the textbook, not gently, loudly. The numbers matter because of what they imply. If the early universe produced galaxies and black holes much faster than the old model allowed, then the entire timeline of cosmic structure formation has to be compressed. Stars formed earlier, galaxies assembled earlier, black holes grew earlier. The chemistry of the cosmos, including the elements that life depends on, was produced earlier. Some of those elements, the heavy ones like carbon, oxygen, and iron, are forged inside stars and only released when those stars explode. If older models are wrong about the timing, then the timeline for how soon the universe could have produced the ingredients for life anywhere in the universe is shifted forward by hundreds of millions of years. The cosmos became habitable sooner than anyone thought. That has its own quiet implications for how likely life might be elsewhere. There is also a less dramatic but equally important implication that touches closer to home. The universe we live in is built out of the same physics that built the first galaxies. The same gravity that pulled the first gas clouds together also keeps our feet on the ground and holds the sun together. The same expansion that Webb is now measuring with such painful precision is the same expansion that created the cosmic background radiation, and the same expansion that gave the night sky its deep, dark, infinite feeling. If our picture of that expansion is wrong, then our picture of time itself is wrong. If our picture of how the first black holes grew is wrong, then our picture of how every black hole grows, including the one at the center of the Milky Way, is wrong. The little red dots are not just a curiosity about the early universe. They are a tap on the shoulder from the universe, telling us we have been telling its story with missing chapters. Consider what it means to look at a single pixel of infrared light and have it argue with the entire model. The James Webb Space Telescope takes the faintest glimmers of light that ever reached our corner of the universe, splits them with spectrographs into the colors that make them up, and turns that into a story about when the light began its journey, what kind of object it came from, how heavy it might be, how bright it might be, and how vigorously it might be growing. Every pixel of every deep field carries hundreds of those stories. And those stories, when multiplied together, are now telling us that something is uneven between what we saw coming and what we are seeing arriving. The map of the universe is being redrawn in real time, and the redrawing is not small. What makes this moment feel different is that the cracks are appearing not just in one corner of cosmology, but in several at once. That is when a field starts to consider the possibility that the cracks are connected. Maybe the unknown mechanism that explains why the early black holes are so heavy is the same unknown mechanism that explains why the expansion rate looks different at different cosmic ages. Maybe the same missing ingredient shows up in both places, just dressed up in different forms. That is the dream of every working scientist. One beautiful idea that fixes several stubborn problems at once. It is also the kind of dream the field has chased before and missed. The Hubble tension, in particular, has been chased for a decade. Every promising explanation has hit a wall. The deeper question, the one astronomers are still not eager to say out loud, is what happens if the standard model really does break. There are options that are uncomfortable and options that are thrilling. The uncomfortable ones include the possibility that there is something seriously wrong with how we have been interpreting the redshifts of the early galaxies. Maybe a fraction of what we are seeing is not at redshift 14 at all, but is instead light from much closer objects that have been contaminated by intervening effects we did not expect. The thrilling ones include the possibility that the early universe was a stranger, more violent, more black hole-dominated place than anyone thought. A place where gravity got ahead of fusion, where light first arrived not from gentle stars but from voracious singularities surrounded by glowing plasma. Either possibility changes the shape of the story. Both options are being seriously investigated today. The part nobody is talking about comes into focus when you put these threads side by side. The early galaxies are too big. The black holes are too heavy for their hosts. The expansion rate cannot agree with itself. The little red dots may not be galaxies at all. The Hubble tension is not going away. Each piece by itself is interesting. Together, they form a pattern, and the pattern says that something fundamental about how the universe grew up is wrong, or at least incomplete. That is not the same as saying physics has stopped working at one particular spot in space. It is saying that the rulebook we have been using for the largest scales in nature is being challenged at every page, by the same machine, in the same pictures, over and over. Right now, the most sensible position to hold is that we are watching a field in motion, not a field in collapse. Cosmology is not finished, it is being rewritten. Webb is the pen, the little red dots are the punctuation marks, the Hubble tension is the errata page, and the people who study the universe for a living are working through what the rewrite will look like. Some of them will be right, some of them will be wrong, beautifully wrong, and the process will keep going until the rewrite is clean. But for a public that does not live inside academic papers, the takeaway is simpler and stranger. 3 years into the operating life of the most powerful infrared telescope ever launched, the universe it was supposed to confirm has surprised everyone by behaving a little differently than expected. The first galaxies came in hot, the first black holes came in heavy, the expansion came in awkward, the little red dots smeared the line between stars and quasars. Every deep field carried another little crack. The cracks are accumulating. The cracks are not yet a collapse, they are an invitation. A quiet, slightly unsettling invitation to imagine the cosmos in a new way. And that, more than any single measurement, is the headline from Webb so far. The sky is not done teaching us. It is not done surprising us. And the surprises are arriving faster than the explanations. That is what makes this moment feel closer to wonder than to alarm. Every few years, a new instrument opens a new window. Each new window changes what we think we know. Webb is simply the latest, and unusually loud. It is showing us a universe that is still in motion, still reshaping our understanding of itself, still delivering news at the most distant edges of space and time. The little red dots are not just anomalies. They are letters from a cosmos that has not finished introducing itself. And whether the letters turn out to mean that physics breaks in one specific place, that the early universe was stranger than we thought, that black holes led the way before stars, or that our models just need a measured overhaul, the fact that we can read those letters at all is the most surprising part. Because when Webb finds something that looks like physics stopping, it almost always turns out to be physics doing something we did not know yet. That is the lesson, that is the pattern. And it has happened enough times across the history of astronomy to be worth trusting. The little red dots are not impossibly strange. They are unexpectedly early, unexpectedly heavy, and unexpectedly hard to fit. That is exactly the kind of thing that, in the past, has opened new chapters in physics. Roughly 100 years ago, observations of galaxies flying apart gave the world the expanding universe. Roughly 60 years ago, observations of the cosmic microwave background gave the world the Big Bang as a precision science. Roughly 30 years ago, observations of accelerating supernovae gave the world dark energy. Each of those began as a surprise. Each of those looked briefly like physics stopping. Each of those turned out to be physics breaking through. That is the quiet bet the field is making now on the Webb era. The little red dots will turn out to be something. The Hubble tension will turn out to be something. The overmassive black holes will turn out to be something. Maybe they are independent surprises. Maybe they are faces of the same deep unknown. We will not know for sure for some time. But we already know that the sky keeps delivering messages, and Webb keeps reading them. The mission has enough fuel to operate well into the 2040s, with the team hoping to stretch operations as long as possible through careful budgeting of propellant and power. Webb is not going anywhere soon, and that means there is still time. And one day, possibly soon, possibly slowly, a researcher somewhere will publish a paper that turns the cracks into a door. That moment has not happened yet, but the data is arriving. The door is forming. And the universe, as always, is older and stranger than the words we had prepared for it. Subscribe to Galaxy Sphere for the next time Webb sends back a picture that turns out to be more than a picture, and drop a comment below telling me what you would call the cosmic dawn if you had to rename it, because the next mystery is already on the way, and we do not want you to miss it.